Hello, everybody. If you could slowly take your seats, we're going to start our afternoon session, where we're going to talk about the pattern effect in the recent historical record. And we have two great talks, one that is focused more on the SST pattern and one that is focused on the radiative response over the recent historical record with a focus on instruments, models, model comparison. And our first speaker, who flew here from Boston actually, is Kris Karnauskas of the University of Colorado, who's going to talk about a review of SST pattern evolution in the instrumental record of the 20th century. Kris, take it away.
All right, thanks. Yeah, I knew they invited me because they thought I was local and it would be free, and so the joke is on them. Yeah, but seriously, thanks to Christy and Maria and the whole SOC for organizing this great workshop. And for this talk, yeah, a lot of input came from other people, including Christy and Maria and Kyle and a bunch of other people on the SOC, as well as Sloan Coates, John Fasulo, and Rob Wills. So some of the talks this morning really did a nice job setting up the fact that the pattern of SST really matters for these big picture things like equilibrium and climate sensitivity. And so my charge is just to go through a little overview of what we can say about that from the perspective of observations since about the mid 1800s. All right, so I'm just going to go through actually kind of a little bit of a detailed background on instrumental SST records, because I think we use them, but we may not all be on the same page about where they come from and how they're built. And then we're gonna take a quick look at some SST trend maps from these instrumental records. And since I love the tropical Pacific, we're gonna sort of zoom in on that a little bit. And then we'll look at how the instrumental SST trends compare to CMIP6 models. And I'll give some words on physical mechanisms that may be driving SST trend patterns and some potential challenges that coupled models, the latest generation of coupled models, may still have, with a focus on the circulation of the Pacific. And then I'll end with some open questions. Okay, so these, what do we get from these instrumental SST reconstructions? Well, a lot actually, right? I mean, they're global, monthly, gridded. They're pretty much everything we want to be able to work with. They're a few hundred megabytes. You can download them freely. Everyone can do it. What could go wrong, right? So they really started, oops, I keep hitting the wrong button. Around 1854 is when most of them won't go back before 1854, because that's about when the international community sort of established a process for collecting shipboard observations that are being taken by volunteer observing ships out in the ocean. And that's good timing, it turns out, of course, because that's right around when CO2 began to really trend upward. That's a bit of a circular argument, because it started trending upward because of industrial activity, and all those ships were out there that were collecting observations were also moving goods around as part of an industrial revolution that was ongoing. Unfortunately, we have paleoclimate as part of this workshop to help fill in what was going on before that, because by the time our instrumental records were started to be built, things were already changing beneath our feet. Okay, and so, the sort of backbone of these instrumental records are ship-based observations going back to the mid-1800s. And clearly, this is not a static observing system over time. It's certainly not one that someone interested in the tropical Pacific would have ever designed. You can see we still have major gaps which have been helped by other observing systems over time. And it's not such a big deal after 1981, when we have AVHRR and other satellite products to fill in that global view. And also arrays of moorings that were deployed throughout the tropical oceans, including Tau. And of course, throughout the 2000s, the Argo array started to really fill in with unprecedented spatial coverage, which is amazing. Nearly 4,000 floats. That's the map from last night I downloaded, and it shows a point where everywhere where there is actually a profile taken, like within the last 24 hours or something. It's not a point everywhere there's ever been a profile. It's a point where there are actually floats right now. So it's kind of amazing. Fortunately, we didn't put them out there in 1850. We started in 1999, but it certainly is giving us a lot to work with. So, you know, all of these sources of data all by themselves, if you wanted to actually characterize the SST variability and change over this time period, you know, they're not that just out of the box. They're not useful for doing that. You need to. Therein lies the cottage industry that's sort of developed that puts together these instrumental reconstructions, and they all have their own machinery to do that, to essentially funnel some or all of these observations into a gridded product. And all the funnels are different. So if you were to try to do this yourself, this is just a very impartial, you know, not incomplete list of some of the myriad choices you would have to make. And some of these are really big issues. For example, how do you choose which data sets to include? So are you going to be a purist, and are you going to only trust in situ observations, or, you know, a maverick and you know, throw in Argo, like the latest NOAA extended reconstructed SST version 5 actually includes Argo, or like one of my postdoctoral mentors, Alexei Kaplan, and say, okay, well, let's do something with the ship-based observations over that period of time, and then simply append the satellite record onto the end. So there's just a million ways to do this. And maybe that's a good thing that we're doing many of them. But how to interpolate and fill in the gaps, you know, and you look at the ship-based observation maps, those little thumbnails over on the left side, it's pretty clear we have a big gappy record. And most of them depend on some kind of an EOF-based approach, where essentially they might do something like an EOF analysis on the satellite record and then take all of the scattered points in space and time earlier in time and project those on a large number of modes to fill in what the whole world was probably doing based on the data points we have combined with the EOFs from the satellite record. So it's all some version of that, actually. There's a million ways to do that too. And then another big issue that, you know, you're a little subjective, but how little data is too little data? For example, like in the 1860s, clearly have very little data anywhere in the world except maybe a line in the Atlantic Ocean. What about the Southern Ocean? Even in the middle of the 20th century, there's still very little data to draw from in the Southern Ocean. And one of the things about EOF analysis, if you do this, you know, you can actually extrapolate as much as you want to, as much as you interpolate. So as long as you have some basis in some period of time where you had information all over the globe, you can get that information all over the globe by projecting onto EOF. So in some cases, these are largely guesses. And I'm not saying they're bad guesses, but we need to keep in mind that oftentimes it's not constrained by a lot of data, especially in the Southern Ocean. In fact, Alexei Kaplan's product simply blanks out the Southern Ocean. It's not worth providing it if there's not enough data in some cases, but the other ones provide it. So here's a bunch of other, I'm not going to go through line by line here, but like, how do you deal with QC? How do you account for the fact that some of these observing systems change over time? New ones come online at different times in the period. How do you deal with spatial and temporal aliasing? Sometimes some of these platforms are actually measuring temperature at different depths in the water, like satellites measure roughly the skin. You've got tow moorings that have a thermometer at 1 meter depth. And then Argo, they'll usually take anything within the top 5 meters. So these are all different potential biases that need to be corrected for. Also, in the middle of the 20th century, at some point, most ships switched from measuring the temperature of a bucket of water on the deck to measuring the temperature of water in the engine room intake. And how long did the water sit there, and all this stuff. So there's a lot of corrections that need to be done. And actually, a paper that gave me nightmares for about a week was the one by Chan and Peter Hoybers that identified that you could actually kind of group biases according to the country of origin that the ships came from. So all of these, sort of human level, differences in methodology and measurement and so on can really affect these things. And how do you quantify and convey the uncertainties to the users? Okay, so now that I've instilled all of that confidence in these instrumental SST products, let's take a look at some of the trends. And so these are just the straight up linear trend over the period 1870 to 2019 in 4 of these common instrumental SST reconstructions. And the global mean is roughly the same in all 4 of them, which isn't shocking. And if you squint really hard, bear with me, if you squint really hard, you might be able to see that the ocean is warming. Okay, so that's pretty obvious. And in fact, the trends are statistically significant almost anywhere because it's 150 years, and it's going to pass significance pretty easily, except where it's very close to 0 because it's switching sign, or some of these cooling trends in the equatorial Pacific, actually, depending on data set, are not necessarily significant at statistical significance levels like 95%. But I would, since we're here to talk about patterns, I'd submit that just because a trend is statistically significantly different from 0 doesn't mean it's significantly different from a trend in a neighboring region. So, it doesn't necessarily mean we can say enough yet about trends from these maps alone, or from patterns in the trends in these maps alone. So what I've done here is just taken those 4 trends and removed the global mean, so to try to sort of expose the pattern relative to the global mean of the trend. And it's obviously challenging. So what I decided to do to try to show you where they agree and where they don't agree is I'm just going to say, okay, any grid point where all 4 agree on the sign of change, we'll color it 1. And if they don't agree, if they don't all agree on the sign, we're going to not give it a color. So that's what we have here. On the left side is, it's red if it's positive in all 4, and it's blue if it's negative in all 4. And so we know what's going on. The ocean is warming. It even captures there's even agreement on the warming hole or cold blob or whatever you want to call it in the North Atlantic. But in the relative trend where we've removed the global mean, there's some agreement in the Indian and Atlantic Ocean, but there's a whole lot of patchiness throughout in the Pacific, and a whole lot of white throughout the Pacific, which means that not all 4 actually agree on the sign of change. So that's 1870 to 2019. This all depends on when you start your record, when you start computing the trends. If we jump forward by 40 years and do the trends from 1910 to 2019, the left still looks the same. The right one, the relative trend, starts to fill in with some blues around the Pacific, including in the central equatorial Pacific. Not a lot of other changes elsewhere. If we jump forward another 40 years, 1950 to 2019, the Indian Ocean now, it's all warmer. It's all warming at a rate greater than the global mean. And the Pacific is starting to take some shape. And then, of course, if we sort of ludicrously jump forward all the way to 1990 to 2019, you start to see some familiar faces throughout the Pacific. And of course, some of this may be owing to internal climate variability. And that's actually something that, so this is a slide contributed by Rob Wills, and this is something that Rob, UA, Christie, and others have been working on, that has actually identified a few regions, including in the Arctic, the tropical Pacific, and around the Southern Ocean, where when you compare it to internal variability in a large ensemble of climate model simulations over the period 1979 onward, these are regions that are very unlikely to have occurred by chance. And I construe that to mean not due to internal variability, although it could be other things, but not due to internal variability. And the eastern equatorial Pacific has some regions in there that are not likely due to chance or internal variability. And speaking of short records but well observed periods of times, that's sort of like the altimeter. Should call them altimeters anonymous. This is a short record, and it's not SST, but it is related to SST. This is largely a fingerprint of ocean heat content, and they're seeing this. The sea level rise community is seeing very similar features, including an east-west gradient in the trend in the tropical Pacific. And when John Fasulo and colleagues have done analyses comparing that, the observed altimeter record in the sea surface height gradient across the tropical Pacific to unforced climate model simulations, it's also looking very unlikely to be by chance. So what's becoming clear is that even in these short periods of time with really good quality observations, there is some anthropogenic signal in there. Okay, so if we focus on the tropical Pacific a little bit more, it seems from I just drew up these plots very recently. So these are covering 1900 to 2019, a common period of time between the four, and they all show a strengthening of the zonal SST gradient in the tropical Pacific to various degrees. And I bring this up because some of the previous talks did highlight that that is a key feature in terms of the Green's functions and climate sensitivity being sensitive to what's going on, especially in the Western Pacific. There's big differences in terms of the magnitude of warming in the Western Pacific, but again, they all do show some strengthening in the gradient of SST across the Pacific, even though the ERSST, the blue curve in the upper right-hand plot, still shows warming in the Eastern Pacific. The gradient is still strengthening. And that actually reminded me of a paper about a decade ago by Amy Solomon and Matt Newman, where they came up with a fairly sophisticated way, not just linear regression, but a sophisticated sort of multivariate way of removing the ENSO signal from the records first, and then computing the trends. And that's what you're seeing there. The first stack of plots are just the 4 SST trends from the instrumental records, just straight out of the box. And then on the right, it's after removing the ENSO signal. And what they concluded was that when you remove the ENSO signal, you see a lot of commonality across the tropical Pacific in terms of the shape of the trends and magnitudes. And it does come down to their individual estimates of ENSO variability that kind of accounts for the differences between them. I'm not really sure why this didn't settle the score a little bit more, but it's out there. And I think that's a very important analysis, especially since we're talking about a place that has this huge source of internal variability being ENSO.
5 minutes.
Okay, so when we compare, and others are going to talk more about models, but when we compare these to CMIP6 models, the global mean is remarkably similar. Again, not shocking. When we difference them over the same time period, 1870 to 2014. And Maria reminded me to remind all of you that just because even if we had perfect models and even if we had perfect observations and even if we perfectly knew the forcing, we would not expect this map of the difference to be 0 everywhere because we do have internal variability. Nonetheless, over this 145-year period, there's been a lot more warming in the CMIP6 multi-model mean than in the mean of the instrumental records in the tropical Pacific. And in fact, the equatorial Pacific writ large is sort of a spot that accounts for a lot of the difference in the trends. This is just an EOF analysis of the trends across the 51 models. And so it highlights regions that explain a lot of the intermodal differences in the trends. And interesting enough probably to the pattern effect communities that the tropical Pacific and the high latitudes really seem to be places where there's a lot of variance in the trends across CMIP6 models. So mechanisms, I mean, there could be entire workshops about various mechanisms in different regions. I'm just going to say a few words about the tropical Pacific. And this actually goes back to when I was a postdoc at Lamont, and I heard of this guy, Pedro D'Anizio, who was I think at the time a graduate student at the University of Miami, working with Amy Clement, and he wrote this nice paper in EOS back when it looked like that. And it was really trying to reconcile the different views. He brought together Amy Clement and Gabe Vecchi, sort of the, if you will, ringleaders of these two camps that were in a very fun, friendly, exciting way going at it about like how do we expect the tropical Pacific to respond to radiative forcing? How should it respond? And then bring in models and observations to see what it looks like. Well, to grossly oversimplify the two different views, there was one atmospheric centric viewpoint that sort of used a Heldon-Soden scaling argument that led you down the path to say that, okay, the Walker circulation is going to slow down. Ocean be damned. The Walker circulation is going to slow down. And of course, that's going to bring about a weakening of the zonal SST gradient that would reduce the upwelling in the East Pacific and so on. The ocean-centric perspective, well, that was Amy Clement and her Kane-Zibiak model saying, well, wait a minute, there's mean upwelling in the Eastern Pacific. In that context, that's actually going to slow the warming in the East Pacific, and then the Bjerknes feedback would take off in the opposite direction, leading to a stronger zonal SST gradient, even though you're just throwing on uniform radiative forcing. And like Pedro, who fortunately is now a colleague of mine in my department at CU, I was at the time also interested in trying to reconcile these different views, and it seemed like a paradox that the SST in the annual mean, the SST and SLP gradients were going the opposite sign from one another in the trends, but their seasonality were at least in phase, the seasonality of those trends. And in fact, they were in phase exactly the same way that Amy Clement's paper predicted that they would be. So it seemed like there was some counterpart in reality to both of these. It was really hard to prove, it's still really hard to prove them wrong. And so one last thing, in recent years, I've been thinking a lot about a potential role for the equatorial undercurrent, going beyond just upwelling in terms of a role for the tropical ocean circulation in shaping these patterns. And if that's true, then the models might be in a little bit of trouble. Going back to CMIP3, the dark ages before Netflix and Python, the EUC, the equatorial undercurrent in the Pacific, was really weak compared to observations. And it seemed to be directly related to how high resolution the ocean model was. And there's been a lot of progress going from CMIP3 to CMIP5, like a quantum leap, in fact, and then a little more progress to CMIP6, but they still have a long ways to go to meet up with the observations. So I just want to do close with a thought experiment with you. So if you think about this is a tightly coupled system, the ocean and atmosphere in the tropical Pacific. And so, but let's widen our aperture a little bit, not just think in one dimension, but like across different regimes in the tropical Pacific. What should be the relationship between the easterly trades and the eastward equatorial undercurrent? What should be the sign of the functional relationship there? And you're probably thinking, positive. You speed up the trades, you speed up the equatorial undercurrent. Well, in the Western Pacific, that's true, says ocean reanalysis products, wind-forced OGCMs, tau moorings, and yeah, even CMIP5 models. But in the Eastern Pacific, they go the other way. In the Eastern Pacific, it's actually the downward momentum flux into the ocean from changes in the trade winds that seems to be winning out over the pressure gradient, and the models fundamentally get this wrong. This is like figure 35 from Sloan's paper in Journal of Climate. So I don't know if a lot of people have seen this, but this is showing a way in which the latest and greatest climate models are mischaracterizing the behavior, the coupling behavior between the ocean and atmosphere in the key region of the Eastern Equatorial Pacific. And so I think that might be kind of a big deal when you're trying to think about how is this system going to change in a coupled way as well. And so, I look back at the SST trend and say, well, there might be something going on there in the real world. And it's, when you compare it to the models, maybe it's not so surprising that they're not getting the same answer. All right, so my key open questions, kind of going back to pattern effects, some of the regions of the world where we have poorly constrained observations or a ton of internal variability, these are unfortunately the places that you're all here and very interested in, based on a lot of the stuff that we saw earlier this morning. Southern Ocean, high latitudes in the tropical Pacific. So are the instrumental records long enough to understand the role of internal variability? We clearly need to do a better job understanding uncertainties and why these different instrumental records are giving different answers in important regions. And except perhaps for large ensembles, are the historical simulations among the different CMIP 6, for example, models long enough in the presence of very low frequency variability, like beyond decadal? And so that's a poster plug. I have a poster about that later today. And so I think we need to work hard. The sort of dynamics community needs to work hard to understand these model biases and the representation of the physical processes. And then I'll throw in my last point is to throw in a plug for embracing other well-observed variables, even if it's at the expense of record length, because these are really, it's been argued that these are, something like sea level is a really robust indicator of ocean change, and it gets around some of the issues we have with SST. So I'd be happy to take any questions if there's time.
Hi, Flavio Lehner from Cornell University. Very nice talk, Kris, thanks. You showed this improvement from CMIP 3 to 5 and 6, but only a marginal one between 5 and 6, and you briefly mentioned resolution. And so my sort of broad understanding is that resolution hasn't changed much from 5 to 6 across models. So have you, or has anybody looked into high resolution model experiments, even coupled? Does that improve things further?
Yeah, so like a number of things come to mind. I mean, I've taken just ROMs, like an ocean only model, and done a set of experiments where all I do is keep cranking up the resolution, and the equatorial undercurrent actually speeds up when I do that. The ultra high resolution model from from South Korea, from IBS, the Axel Timmermans ultra high resolution of the CESM. Sorry, I'm kind of mischaracterizing it. Malte, you probably know more about it than me. It has a really nice equatorial ocean circulation, but within the CMIP6 ensemble, I've done that same plot where it's on the x-axis, it's ocean model resolution, the y resolution near the equator, and on the y-axis, it's speed of the equatorial undercurrent somewhere. It still goes like this. So even within the CMIP6 ensemble, there's still enough diversity of resolution that you can just see the dependence on resolution. And velocity isn't everything. A lot of them are getting the right, close to the right transport. It's just more diffuse and kind of, so they might be getting the right water, but velocity does matter for some things that's distinct from transport, like shear and some of the dynamics. So yeah, but you're right. I don't think there's been a huge increase in the resolution from 5 to 6, and I think that's why we're kind of still in that state. Yeah.
There's a question online from Paolo Ceppi. Do any of the SST reconstruction also assimilate SLP?
SLP, no. I mean, not the main sort of SST reconstructions, but for that, what you get from so all of those, Hadley and Kaplan and NOAA, they also tend to have an SLP reconstruction that was produced in a very similar way, just for SLP. But that's where reanalyses like the 20th century reanalysis and other longer term reanalyses come in, as you can assimilate those, and then you're kind of in a negotiation between a model and observations. But no, those SST ones don't know anything about SLP observations, as far as I know.
Another question online.
Let's have one in the audience.
Okay, we'll take the online question after the one in the room right now. Go ahead.
Real kind of surprise to me when I first saw it, and I wonder if do you think that there's the potential for more surprises lingering, that we might have, some basic uncertainties still present there?
Like even within satellite data? I mean, I'm not familiar with that study, but
Tom Carr, his studies show that during the hiatus interval, that in fact there was a 1/10 of a degree Celsius more warming globally than had previously been estimated as a function of calibration of buoy data relative to satellite data.
I see.
And so, if you can do that in the 2000s,
yeah,
for the NOAA product, which is one of the headliner ones, is there the potential for kind of lingering issues elsewhere that might crop up? I'd be interested in your opinion.
Yeah, no, I get it. I mean, I'm guilty of just assuming satellite data is pretty rock solid, but of course, all the uncertainties and methodological choices I talked about with the longer term instrumental reconstructions, the satellite community has the same sorts of discussions and workshops about how to deal with that. I mean, they're not really directly measuring SST, so they do have to make some choices, and like you said, ground truth it with mooring data. And I'm not really familiar with the uncertainties of satellite data like with the instrumental records, but I wouldn't really be surprised. I would assume that our ability to I would hope and assume that our ability to characterize the trend since like maybe 1982 would be pretty good, especially if there's big changes in magnitude or differences in magnitude of the trends across different regions, but maybe not. I don't know.
So we'll take this online question and then we'll go on to our next speaker. So a question from Diego Jimenez de la Cuesta. Thanks for the great talk. Is there a proposed concrete way, apart from models, to recover the Southern Ocean from the early period? Proxies?
Well, I mean, I feel like I should just punt that one to the paleoclimate community. I mean, there's just so little data from the Southern Ocean, and yeah, aside from using EOF style approaches of filling that out, I don't know. I put that as a question. I think on the previous slide I said, will we ever be able to resolve the issues in the Southern Ocean? That's not quite my bailiwick. I don't know. Maybe the paleoclimate community can speak up on that one.
Great. So let's link Kris one more time.
Our next speaker, I can just do it from here, I guess. Our next speaker is Norman Loeb from NASA Langley Research Center. He's the principal investigator for the CERES project. And I actually don't know if you go by Norman or Norm.
I've been called worse. Either is fine.
Well, in any case, take it away.
All right, so advancing is just this little thing here. Okay. All right, I'm going to talk about top of atmosphere radiation. I'm going to be focusing on the series record primarily since 2000. So just to put this period into context, I look here at two variables that arguably have a large connection to patterns of sea surface temperature, the Nino 3.4 index and the Pacific Decadal Oscillation. And so the decade's been interesting. We've had, prior to 2000, we had the 97, 98 El Nino that's not on here, but that was followed by a fairly prolonged period of La Nina. And we had a little bit of these oscillations between positive and negative El Ninos. The PDO during this period has been solidly negative. And then things really went crazy. In 2014, the PDO flipped to positive, and we had the 2015-2016 El Nino, and then PDO flipped back to negative. And things have been sort of quiet. We're kind of in a La Nina phase now. And when you look at the Argo data, this is looking at 2004 onwards, you could see that it's been predominantly negative, the near surface temperatures, up to about this magical 2014 period. And then you had positive anomalies that coincided with this change in the PDO. But they've remained positive. It hasn't gone back, which is kind of interesting. Even though the PDO index went back to negative in 2017, it's still negative. The near surface trend is about 0.2 degrees per decade. This is the spatial pattern of the SST trend for the series period from March 2000 to December 2021 on the left. On the right is the corresponding shortwave flux. And I'm assuming there's a mouse here that could work. Oh, good. Okay, you can see that. Yeah, okay. So, yeah, the interesting thing in this period is all of this warming in the Eastern Pacific, very prominent. You also have corresponding to that in the shortwave on the right, this area of marine stratus where you had these huge decreases in marine stratus, and that makes sense. Low clouds don't like hot SSTs. And so that makes perfect sense. But beyond that, there's a lot of other areas where you're seeing positive trends in SST that coincide with negative trends in shortwave TOA flux. So there's a real connection between these two. We also had interesting events. We had these marine heat waves, these blobs in 2013 to 2015, and then another one in 2019 to 2020. So that's sort of the spatial pattern of the shortwave flux trends and the SST trends. So then you say, well, can I trust the shortwave 2A flux? So you could look at MODIS, which provides cloud fraction. And so this is taking that region, that box that I showed in the previous slide in the East Pacific, and looking at the cloud fraction anomaly in red and the series shortwave 2A flux anomaly. And you can see how things, they track each other pretty well. You don't expect them to track perfectly because the shortwave flux doesn't just depend on cloud fraction, it also depends on optical depth. But you could see that to first order, most of the variability is explained by cloud fraction. And then you see around 2014, this drop that's in both data sets. So that's pretty robust. And you can also look at the series instruments on different satellites. There's series instruments on Terra, Aqua, Sumi MPP, and NOAA 20. They were all launched at different times. But if you put them on use a common climatology, it's sort of, whoops, it's a short period. How do I go back? Previous. I won't touch it because it's going to go forward. So if you have them on the same scale, you could see that these different instruments on different satellites are all really showing the same story at the monthly level. So the 1 sigma standard deviation is on the order of 0.3 of a watt per square meter at the monthly scale. And they're tracking each other. You're not seeing drifts of one relative to the other. And one of the alarming things in my mind is these trends. So on the right here, these are the trends that we're seeing in EBAF, 0.7 watts per square meter per decade for absorbed solar radiation. The OLR increased 0.27 watt per square meter, so this is shown here as negative because the fluxes are positive down. And the net Earth's energy imbalance increased 0.42 watts per square meter per decade. That's really dramatic. So if you take the average for the first 5 years, from March 2000 to February 2005, the imbalance was 0.44. Compared to the last 5 years of this period, it's 1.14. So that's 0.7 watts, which is essentially a doubling of Earth's energy imbalance over this period. It's pretty scary, pretty large. So can we trust that? How good are these results? So we could look at the Terra period on the top, looking at trends for the Southern Hemisphere, Northern Hemisphere, and global, just for the series instrument on Terra. And I'm looking at the trend as a function of record length. So starting in March 2000 and looking at trends for a 5-year record, 7-year record, et cetera, all the way to a 20-year record. The gray shading is a 95% confidence. So you could see when you have a short record length, the trends bounce around until you get, depending on the region you're looking at, but once you get about a dozen or so years, it stabilizes and it eventually exceeds the 95% confidence in the Southern Hemisphere, Northern Hemisphere, and global. And what's remarkable is the trend in the Southern Hemisphere and Northern Hemisphere are almost identical, which is kind of a curiosity. So then you could say, well, how do the two longest series records from Terra and Aqua compare? So the bottom three show the difference in trend between Terra and Aqua, starting from July 2002 when Aqua launched, as a function of record length. And you could see that if you look at the full record, the Terra and Aqua net flux trends are consistent better than 1/10 of a watt per square meter per decade, which we never would have dreamed of when we launched these. So it's quite pretty good agreement. And we've also compared series EBAF with Argo in situ, and they're also extremely consistent. So this large increase in Earth's energy imbalance that I showed in the previous slide, I think is a really robust result. We've also looked at trends in ERA 5, as well as a version that uses the same model run in AMIP mode. And what we're finding is kind of a surprising result. So the left plot here shows the net flux trends from series, and you see that big signal in the East Pacific in the low-level clouds. It's not there in the ERA 5, not at all. It's sort of there in the AMIP, but it's actually in the wrong place. So I was pretty surprised by that, and it just tells you that user beware with reanalysis in terms of trends because of changes in observing system. You can have some real problems. That said, if you detrend the data in the reanalysis, it tracks pretty well in terms of the monthly variability that you get with series. Andrew Dessler looked at cloud feedback. How robust are the cloud feedbacks that you get from observations? So he looked at using series data together with 2 reanalyses. At the time, it was ERA interim and MERA 2. And the period here is from March 2000 to June 2011, so it's a short record. So he looked at 7 different data sets and 2 reanalyses, and the results, and he used 2 different methods of calculating the feedback. using the cloud radiative forcing and then adjusting for non-cloud contributions. And then a second one that just uses the all-sky fluxes and makes adjustments for non-cloud from that. And what he's showing is that the result does depend on what SST data set in particular. The reanalysis sensitivity here isn't that large. I'm showing the averages here on the right. There is a difference, but it's relatively small. There's a larger sensitivity to what SST data set you use, but he makes the point that you're still getting a positive feedback regardless of what record you're using. So there is some sensitivity in terms of the magnitude. Okay, so that's sort of the quality of the observations. Now I'd like to turn to comparing models and observations. Because we had such a large signal in the series, we wanted to see how well the models do. The problem is the forcing ended in 2014, right when the fun was happening. It was after 2014 that everything took off. So, well, I was able to get 7 different groups to extend the AMIP simulations so that we could look at that interesting period. And so these are the results. It's kind of cool. They did pretty well, some of the models. Certainly the HAD-GEM did really well at the end of this period after 2014, when you see that big dip in reflected shortwave. The Canadian model did well as well. ECAM 6.3 didn't do very well. You could see how the red line and black lines don't agree after 2014. And then since I'm here, I might as well talk about CESM2. Actually, it's kind of in the middle in terms of agreement with series. It's not too bad, but there are models that I think did better. GFDL did really well in this comparison as well. We also looked at the spatial patterns of the differences, and to do that, we used the post-hiatus, which was for July 14 to 2017, just 3 years, minus the first 14, what I'm calling hiatus. And you can see the SST differences there on the left, and the East Pacific really large. And the right shows the series results for shortwave, longwave, net, and then using the average of the 7 models. And they did pretty well. You see the East Pacific there, the large change that we're seeing, the negative difference in series. It's there in the 7 model mean, but it's more muted, so it's not quite as pronounced. In the tropics, you see the shift in convection there. That's nicely represented in the models, but maybe actually a little bit too strongly in the models. And then the long wave is looking pretty reasonable in terms of at least where things are changing. And then the one I think is most interesting to me is the net. You can see how there's so much cancellation between the shortwave and long wave, and what's left is primarily changes in the East Pacific, where you have the marine stratus clouds, as well as this line along the equator. So it really tells you that these changes are really dominated primarily by low clouds in the net. So these trends that we're seeing in EEI, there was a study by Raghu Raman who really wanted to see, his basic question is this all just due to internal variability? And so what they did is they looked at ensemble climate simulations, just looking at unforced. And when they did that, they couldn't get the models within the observational uncertainty. It's only when they added forcing that they got it. So you can see here the black line in the middle, close to 0.4, is the series trend. The dashed lines here are the 95% confidence interval. And then the green here is the various results from the different models. And so they concluded that the series trend that we're seeing is exceptionally unlikely to be explained by internal variability alone. The models only fall within the observational uncertainty when they add the anthropogenic forcing. But one thing that struck me when I saw this is they just barely get there. The models just barely get into this 95% confidence range when you add the forcing. None of the models are really coming close to this 0.4 value that we're getting. They're all kind of lying close to 0.2. So they're in the uncertainty, but just barely. So to me, that's kind of an interesting question. Why? The 7 AMIP simulations that we looked at earlier, now I'm looking at not just the EEI, but looking at regressions against surface temperature. So this is what I'm calling the radiative restoring coefficient, or you can think of it as a climate feedback parameter. Looking at the difference in anomalies in net flux minus effective radiative forcing against the surface temperature anomaly. And just to give you a sense of the magnitudes, if we took the period from January or from 2001 to 2014, the feedback parameter we got is about -2 watts per square meter per degree Kelvin. And then just adding 3 years, it got down to 0.5. Dramatic change. And some of the models captured it. The IPSL here in brown is on top of series. ECAM6 is way off. And then the others are somewhere in between. And we also sort of tried to quantify the pattern effect by taking a ratio of these coefficients for these 2 periods. This plot shows that ratio as a function of the difference in the Northeast Pacific region between the post-hiatus and hiatus. And so what you find is that most models have this ratio that's too large, which would imply, based on this result, too weak a pattern effect, as well as shortwave response in the Eastern Pacific that's too weak. And it also would suggest that a model's ability to represent the changes in this relationship between the global mean net flux and surface temperature really depends on how well the model does in this East Pacific region. I don't know if that's a general result or just specific to this period, but it seems like a pretty robust result for this period. There was a nice study, one of the first studies to look at these relationships using observations from Seppi and Gregory, where they looked at observed regressions of SST, EIS, net CRE, and TOA radiation here against the global mean EIS anomalies. And what they found is that decreases in EIS in the Eastern Pacific are associated with positive trends in SST, and that implies positive trends in the net CRE due to reductions in cloud cover and more net radiation coming in. And I think what the real reason for putting these plots in the paper is really because most of this paper was about simulations, but what they concluded was that these results qualitatively support this notion that decreasing tropospheric stability promotes a decrease in radiative cooling through changes in clouds and tropospheric lapse rate that's consistent with their main conclusion is that there's an evolution towards higher effective climate sensitivity in the CO2 forced climate model experiment. So these patterns looked very similar to what they were getting in the simulations.
5 minutes.
Okay. Another study that's sort of interesting that just came out recently, I'm not sure if I'm pronouncing the name right, Chow. They looked at CMIP6 GCM pre-industrial control simulations from 26 models and looked at the distribution of the cloud feedback, lambda, and compared it with what they get from series. And what they found was 85% of these 20-year model segments that they looked at have values that are within the range of series, which is shown by this dashed line, and then the dotted lines are the corresponding uncertainty. So this would say that the models are doing pretty reasonably well. But they also looked at a different thing, which kind of gets at this pattern effect, which I thought was really interesting. They looked at consecutive 10-year periods. They took all of these 20-year periods in the model and they broke it down into 10 consecutive 10-year periods, and then calculated the feedback, cloud feedbacks for each 10-year period, and then differenced them and compared that with what they get from series. They got a very different result. So now this is delta lambda. Again, the vertical line here, the dashed line is series, and they found that only 27% of the results from the models fell within the uncertainty range of the observations, mostly at the lower end, and only 2% of these model estimates actually exceeded the best estimate from what we're getting from series. So based on these results, series, this 20-year period that we get from series was, this is my conclusion, not theirs, but this period was either really weird, really exceptional, or the couple models maybe not doing a great job at representing these radiative patterns. So that could be an interesting question for discussion. They also looked at the two periods regionally, and this gets at another sort of discussion thing, is how do you compare models with observations, especially coupled models? So what they tried to do here is they took period 1 from series, which was first 10 years, and then period 2, second 10 years, and then took the difference and then compared it with these differences they get from the model, but only considering those models where the delta lambda fell within the 90% confidence that we're getting in the observations. And so that's the bottom right plot here. And so they're kind of getting something similar. The sort of main robust feature, or the only robust feature, I think, is that the positive changes in cloud feedback over the East Pacific seem to be robust, but the magnitudes are very different. But it's a very difficult thing to do, to compare one realization over 20 years with coupled models, because of what we heard. These internal variability wouldn't expect to match up, but that's what we have. So how do we use observations to help us understand the models better? So my discussions, why is the observed trend in EEI since 2000 so large? Is it forced climate simulations just barely exceed the lower bound of the 95% confidence in the observed trend? So could you say that the unforced pattern effect is responsible for the large observed trend? Is that effect underestimated in GCMs? Besides ENSO and PDO, what other factors in terms of internal variability most impact SST and radiation patterns? How can observations best be used to assess the realism of SST and Earth radiation budget patterns in coupled atmosphere-ocean GCMs? And if none of those interest you, the last one I'm sure will, because this really we had discussions prior to this with our committee, a steering committee, and I very naively said, well, yeah, if the models don't do well compared to observations, how could you trust their projections? And my gosh, that just sort of sent a flurry of comments. Well, wait, it depends. So it's not apparently not a yes or no answer to this question. So thank you.
Great. Thanks very much, Norman. So any questions? I'd like to field questions from the floor.
Hi, that was a really great talk. Thank you. I just was curious. My sense was that the temperature pattern before 2014 was quite unusual compared to maybe things that we've seen in models or general. Is there a sense that the warming pattern since then has been like a reversion to a more more uniform pattern compared to even earlier periods, or is there a sense that it's a further very different sort of extreme pattern of some sort? Like I'm wondering how far away from the full variability models are in terms of if they're too stable in the sensor or not.
So yeah, the first 14 years, I think the when you include the El Nino, that really caused a big change in the pattern and the radiation. So I would say that the first 14 years might be, if you were going to compare the two, might be more typical than the last. I think that this, and we're still, this is what's a mystery to me. Maybe it's another open question. Why are we still warming, or why aren't we reversing or seeing a reversal in both SST trends and TOA radiation net flux? Because the PDO has shifted back to negative, yet we're still seeing this increase go on. So something seems odd to me, at least in this latter period from 2014, more so than the first 14 years. And I don't understand it. I was hoping I could come to this meeting and someone had explained it to me.
So, Jenny, do we have anyone online at this point? Or?
We do have a question online from Thorsten Martsen. The large trend in EEI is indeed large, but is it the current value which is large, or the early period value which was small?
No, I think it shot up. I think that, including the latter period, it really, the trajectory of EEI, if you look at how it varied, it really kind of ramped up more towards the end of that period in response to the cloud changes primarily.
Hi, Norman. Sorry, I'm Shiv Priyam Raghuraman at NCAR now. Norman, great overview. Couple of comments. I think one thing to Thorsten's point was I actually think the trend of 0.4 was up. If you did it 2001 to 10, it would still be 0.4. So I'm not sure it would be too different. But the first point here about the climate model simulations, I'm not sure if it's all going to be explained away by the response to the SST pattern. I think models might be missing a forcing too, for example, greenhouse gas adjustments for clouds, as well as the simulations we did, plus the existing CMIP6 simulations, don't have the right drop-off in the aerosol decrease, so less aerosols in the atmosphere, less reflection of sunlight.
Well, hold on. Let me ask you that one, because that one we looked at aerosols and we don't see much signal in terms of direct effects. So are you talking about the indirect effect of aerosols or direct effect?
I'm talking about both. So we did see a direct effect, and then indirect effect also we saw a big dip in the liquid water path in MODIS, consistent with the second indirect effect in the northern exotropics. But I'm saying that the updated CEDS emissions data set prior to 2010 is also decreasing more than what the current AMIP and CMIP simulations have. So I think it's still an open question if the models are underestimating the forcing or underestimating the response. But my hunch is it's probably both. Yeah.
Kyle?
And Norman, thanks a lot for the talk. On this first point, this suggests that it may be an SST pattern problem where the couple models just don't capture the SSTs as observed, and that's the reason they don't get the large increase in energy imbalance. I'm wondering if anyone's looked at this exact question within the AMIP runs with forcing, and if so, whether those runs better capture the observed increase.
Well, you mean the SST or the radiation?
The prescribed SST AMIP runs, where if you prescribe the SSTs, I'm wondering if that does a better job of capturing the increase in energy imbalance. Yeah, I believe this study that you showed is just coupled runs.
No, the paper, well, you're co-author on this paper, right? We did the AMIP with observed SSTs. So
did they get the 0.4 pretty well? I thought our paper didn't have forcing changes, but it was like
we had forcing changes up to 14, and then we kept them constant. So right, we had, because they were only available up to 14.
But do you remember if those?
We didn't really look at the trends so much as just the internal variability, but just from the plots I just showed, it's hard to say whether they were in the 2.2 or 0.4 watts just by eyeballing. I should go back and look at that. I wasn't thinking about looking at trends back then, so it's probably a good thing to do.
Good, I'm not crazy. Excellent.
No, you're not crazy.
Thanks.
I'm Lei Chao from Texas A&M University. So really great work.
Oh yeah, okay. Nice.
I appreciate you mentioned our work. So I have more like a comment is we not only compare observations with the CMIC6 pre-industrial control run, I also like compare observation with the couple model with forcing. So like observation is from 2000 to 2020. So I take the couple models from historical run from 2000 to 2014, and then the SSP 585 run from 2014 to 2020. So I combine these two. So I have the coupled model run with the forcing and compare that with the observations. And the result is also not good. So like model is not doing a good job in reproducing the observation, which is different with your results, which compared observations in AMIP. So like more like a comment is like based on this difference, AMIP is doing a good job, but the couple models is not. I feel like the message inside is like our azimuth frag model is already have really realistic physical inside it if it has the observed sea surface temperature pattern fit into the models. But the coupling model issue is the coupling between the ocean and the hemisphere, and that could lead to unrealistic sea surface temperature, therefore lead to fail in reproduce the radiation patterns.
Right. One thing I struggle with, because the AMIP is, I'm not a modeler, so I'm looking at it from my own limited point of view. But I know that the AMIP, you are specifying SSTs, and it's just an atmosphere-only run. And as we heard, when you look at coupled atmosphere-ocean model simulation, you wouldn't necessarily expect it to get internal variability correctly for this particular decade. So I struggle about what I can say from coupled atmosphere-ocean models. And I think your study was useful in the sense in the way you looked at it, you know, because you looked at it statistically. You had many, many realizations, and you looked at the PDF and looked at where the PDF lies relative to the observations. And to me, that seems like gets around some of the problem of trying to get the one realization that we've observed with a couple, because I'm not sure that's an apples to apples comparison.
Just want to follow up on that actually. So Norman, in the figure you showed of ours, the last model is GFDL AM4, 20 realizations of AMIP up to 2020. And that actually does worse than the coupled models. So in some of them. So in some case, even prescribing the same SST and sea ice pattern over and over again of the AMIP period doesn't really get you better for the EEI trend.
Yeah.
I think that was Kyle's question. So I might have to disagree with the coupled model being better or worse off. So yeah.
So I like the discussion that we're having. I also want to acknowledge that we are in our final 30-minute discussion for today. So if we can also invite Kris up onto the stage, and we can open up the questions for both Norm and Kris.
Thanks, Jenny.
And for the
I was getting there, but yeah, I think that's good. So Kris, are you happy to go back up on the stage?
We do have a question online for Norm though. So Kris, you can take your time if you want to walk slowly. This is from Gita. Is there a clear understanding of why some of the models got the 2014 to 2022 behavior right in the extended AMIP runs and others didn't? Could that potentially help explain what's driving the 2014 to 2022 behavior? In other words, it's whatever the correct models have and the incorrect models don't?
Yeah, that's a good question. And I asked my co-authors, who were the people that were doing the model simulations, that very question. And I don't, these models are complicated, and some of the models, it's encouraging. They put in new cloud schemes with aerosol cloud interactions, and those did better. So I suspect, the physics that they've added in could have made the difference of why some did better than others. So I'm not sure I caught the second part of that question. That was the first part.
Let me see. Could that potentially help explain what's driving the 2014 and 2022 behavior? In other words, it's whatever the correct models have and the incorrect models don't.
Right, but that doesn't explain why things are continue to go. I think we're not peeling the onion here. We're just looking at how things have changed. Maybe those models could be useful for unscrambling. I mean, certainly GFDL is one of the models that did really well, and that was what was used in the study that I showed. So, yeah, it begs another question: is should we trust those models that are getting us better agreements when, because the observations, it's the integral of all of these different processes that we're looking at. It's TOA flux is an integral of lots of stuff. And if a model does really well, is it doing it for the right reasons? And can we then use it to unscramble the physics of what is driving change? And those, I think, are good open questions that I don't necessarily have the answer to.
Hey, Norm, thanks for the nice talk. I was curious if you've had a look yet at the series flux by cloud type to try to see which cloud types and changes in clouds are affecting these trends. And is that something that, is that trustworthy?
Yeah,
to look at
oh gosh, Mark, you're so smart. Yeah, I mean, I'm excited about that. I started looking at that, and what I found out, so what I did is I looked at low, middle, high, and then took the low and split it into sort of marine stratus to cumulus transition, and cumulus, using EIS to sort of separate them. And I looked at southern hemisphere, northern hemisphere, because the other thing I'm curious about is why these trends are so similar in the two hemispheres, which is kind of weird. But what I found is the northern hemisphere stratocumulus clouds, those are those trends are robust as far as the signal of the northern hemisphere. In the southern hemisphere is the middle clouds. The middle cloud trends were significant. Now, are they trustworthy? That was exactly my question too. Are they trustworthy? Because I really think, you know, you could look at seasonal cycle, and you should get that. You could look at anomalies, which is a little harder, but trends is the holy grail, you know, because it doesn't take much to trip up a trend. Discontinuity here just really drives a trend. So when I look at series, I have the luxury of having all of these different instruments to compare. Cloud fraction from MODIS, yeah, I don't have that many to work with. So we're in the process right now of using Calypso and CloudSat to sort of, we're using the C3M product to see if we do an apples to apples comparison. If we sample Calypso like MODIS, exactly the same, do we get the same trends? And that's what we're in the process of doing now to see if these trends that I just talked about are realistic. So
look at optical depth as well, or just?
I get nervous with optical depth. I mean, I kind of trust cloud fraction, because what you're doing is you're using many, many different channels, and we're only looking at flux by cloud type daytime only, so you've got the visible and the infrared. I get worried about, I'm very risk adverse when it comes to trends and cloud optical depth. So far I've kind of shied away, and people have asked me that, and I get really nervous. Maybe I should just to see what I get, but it's just calibration is a real issue, and yeah, I'm on the fence on that one. But people were asking me about high clouds. Why am I not splitting high clouds in thin and thick, which is a reasonable thing to do if you could trust optical depth, but no. So thanks, Mark. Jeez, you're
working.
I'm impressed.
Mark, you might want to get back up. This question is, I guess, for Norm or Mark or Tim. Norm, you mentioned that there might be differences between models and observations in terms of the sensitivity of low clouds to SSTs in the northern stratocumulus decks. And there's some work by Tim Andrews and Mark Zelinka and Ryan Scott where you all have looked at the specific, using cloud controlling factors, at the sensitivities of these low clouds to cloud controlling factors such as sea surface temperature and estimated inversion strength.
Yeah.
When you, if you look at the cloud controlling factors and you compare the ones derived from observations to the ones derived from models, how do they compare? Or have you looked at this?
I did in that same paper. What I found was from the observations, at least for this period over the Eastern Pacific, SST by far was had much bigger impact explaining the trends. And EIS did, but it was much smaller contribution. And then the models, if I recall, the magnitude wasn't as strong as what we're finding in the observations. So that was ours. I don't know, Mark, if you have comments. Tim?
Yeah, so in coupled models, like if you do what was it on? In coupled models, if you compare how sensitive low clouds are to cloud controlling factors, it varies by quite a lot compared to observations. And the tricky thing is that you cannot always construct cloud feedback simulated in a model using cloud controlling factor analysis. So it's a little bit tricky. On the other hand, it would be interesting to perhaps, and it's something we've been talking about doing, is explaining differences in the, say, like Green's functions from model to model. Green's function is like basically the sensitivity of globally average radiative flux to perturbations in patches of warming. But these patches of warming will then, the reason they're causing radiation changes in the first place is because of corresponding perturbations and then meteorological factors. So I think this cloud controlling factor analysis could be used to not only understand discrepancies between models and observations, but why different models get different Green's functions.
Yeah, it's interesting.
There is an online question from Pierce, a combined question for Kris and Norm. So Kris, you look like you're falling asleep. So
Kris, why don't you answer it first?
If you imposed all of Kris's SST uncertainty into AMIP, how much would the 0.4 watts per square meter trend vary by?
Yeah, can you repeat that? I didn't quite.
If you imposed all Kris's SST uncertainty into AMIP, how much would the 0.4 watts per square meter trend vary by?
So did you say Kris's uncertainty? I heard Kris's uncertainty.
I think the uncertainty that I referred to between the instrumental SST data sets and the trends.
For those online, they're trying to talk out a solution.
Yeah, I feel like we should just run
them.
the experiment.
Yeah.
I mean, I feel like I've seen papers that have.
Can you talk in the microphone, Kris?
I don't recall who did it, but I know I've seen a paper where they have taken different SST reconstructions, the ones I spoke about, then forced an AGCM with them to see how big the consequences were for the global atmospheric circulation. I cannot recall who did it, but I guess you could then mine those experiments to get that number out of it, but I've never seen someone use those to get that number out of it.
So I'd probably follow up by saying you have to caveat that it's the uncertainties from 2000 to 2020, not going back in time. And I imagine those uncertainties are going to be much smaller than the prior. Yeah. So, but it's still a good question. It's something that could be done, I guess. Someone who runs a model.
There are a few names thrown out right now. Thorsten has looked at this, and so has Tim Andrews. Another one from Amanda Maycock said that, I'm sorry if I mispronounced your name, Angshuman Modak has been looking at this in Constrain.
All right. So Spencer
real
and
quick.
this, is it related to this?
Yeah. There's also Tom Flanagan and Stefan Flegelstaller a few years ago had a nice paper or two looking at two different SST products and how that affected in a AGCM context I think it was the tropical upper tropospheric warming trends, and it was pretty surprising just how much it affected.
Right.
Hi, Charlotte DeMott from Colorado State University. I hope I don't cut off the discussion that's going on here right now. My question is for Kris. It's on a slightly different topic. In your talk, you spent some time talking about the misrepresentation of the equatorial undercurrent as playing a role in setting the east-west, playing a role in changes to the east-west temperature gradient in the Pacific. So my question really is, what is it about, what processes really do you better represent with finer ocean model resolution that improve the representation of the EUC, and is it, maybe something vertical resolution, horizontal resolution? So kind of wide open. What more can you say about that?
Yeah, I haven't gone all the way to sort of picking that apart, but I think I haven't looked at the vertical resolution dependence of this, but it probably could matter. But the biases in the equatorial undercurrent, probably affect mixing, not just advection of water towards, where it's getting upwelled in the east, but mixing, because if you've got a weak, I've looked at CMIP3, CMIP5, and CMIP6 models and sort of how they represent the vertical profile of zonal velocity, for example, and you can get shear and n squared and Richardson number and all that stuff out of there, and you can see the biases are there. So I think there's implications for mixing, and that we know is part of what maintains the cold pool, and if they're undercooking that a little bit, then that probably impacts how they respond to radiative forcing. So yeah, that's what comes to mind. Yeah.
So I sort of have a somewhat related question in terms of both of your talks. When we think about the trend towards a greater east-west SST gradient, right? At least that what was in your patterns to some extent, this cooling of the cold tongue region. And then we think about this TOA imbalance kind of trend as well. And when I think about like a La Nina state versus an El Nino state, I think more of a TOA imbalance when we're gaining more energy in a La Nina state than a El Nino state, right? So I wonder, is there actually a connection here with the inability of our coupled models to maybe get this force trend, and then the inability potentially to represent the TOA imbalance? Am I thinking about this correctly, or do you think there's a...
I'll say a caveat to sort of my talk, and then you can think about what you're going to say, Norman. I guess I'll plug a talk that Ulla Heed is going to give, I think, tomorrow. I don't want to imply that the coupled models are incapable of recovering what we've observed, but in the historical runs they don't. They give basically the opposite answer in the tropical Pacific. But some work that Ulla Heed has published and Alexei Fedorov has shown that it might be a time dependent response, and that so far what we're seeing in the observations is actually the short response, and then the coupled models you seem to be able to get that out of the coupled models, and then sometime in the coming century it does change. But
yeah,
I'll let Ulla.
Oh, I'm glad you said that. I'm actually a co-author on two of those papers.
Oh,
but it happens very much in the abrupt
yeah.
response, right?
Yeah.
In the when you have the transient forcing that's a bit weaker, then you kind of prolong it, and then signal to noise gets trickier. The other thing is it's very model dependent. So some models have a really strong initial thermostat, and some models have in abrupt runs.
Yeah.
But it gets very subtle when you start to put it into the historical forcing context. So I wonder if it should actually be stronger, and maybe those models that have that stronger initial thermostat kind of gets to see Richard Seeger's work as well, right? Like, is this, are the models getting that initial strengthening, if it is a forced response with the correct magnitude? But I was just wondering if there was a nice way to link it to the TOA side as well.
I mean, my point was that I think the ocean component of coupled models may not be even able to give that initial thermostat mechanism a chance.
And by the way, it's stronger in the higher resolution models.
Exactly. So this isn't a problem that can't be fixed either.
Yeah, so the TOA, I think it boils down to low clouds. I think, as I showed, even if you had the SSTs in these AMIP runs, the models had the right sign where the low cloud changes occurred, but their magnitude was too small. So for whatever reason, we're seeing much stronger response by low clouds in observations than the models we looked at. So I think, and it's always been the Achilles heel of GCMs is low clouds. It's been, I think, results were encouraging. They show progress, but getting the magnitude, especially trends, again, trends are tough. There's still room for improvement, I think.
Perfect. Yeah.
Hi, my name's Vince Cooper. I'm a grad student at University of Washington. Questions mainly for Kris. So you showed how when you remove the global mean trend back to 1870, the patterns really don't agree between the different SST data sets. I guess I'm just curious whether we have any confidence at all in just what the patterns are from, say, just 1850 to 1900, that earlier period, and whether it's maybe an issue that these data sets are using kind of different interpolation and extrapolation procedures and maybe aren't necessarily even like dynamically consistent. I don't think that any of them are using like data assimilation. So are they just kind of, making things up and using different methods and they don't agree? And is that, maybe a problem?
Hey Vincent. I don't think they're making anything up. But you're right. They're not assimilating data in the sense of, when we think of data assimilation, because there's no dynamical model there constraining things to what physically can and can't happen, basically. I don't know what the trends look like from 1850 to 1900. I don't think I would dare to look, but if there's that much disagreement over the whole period, I'm sure there's well, I don't know. I mean, maybe they look exactly the same because they had like the same 7 data points to constrain them to. I don't know. That'd be an easy thing to do. I could do quick. I don't know. It's a good question.
Thanks.
Yeah.
We have a question from Claire Desser to Norm. Since low clouds can also cause SST anomalies, the response in AGCMs to observed SSTs doesn't have to reproduce the observed low cloud trends. Do you agree?
So, okay, that's a good question. And I think I'd struggled with that question before this paper about using the AMIP. Was this feedback? You're not really feeding back, you're using the observed values. And I think David Painter looked at this and he was showing fairly similar results in these. Essentially, I think he was taking the output from coupled models and putting it into an AMIP run, and then looking at comparing the feedbacks. And I think he concluded that he was getting the same result, which gave him confidence that the AMIP results were at least not too far out. So I'm not sure if Priyad, did you have any? You were working with David. You might have been involved in that study. I don't know.
I think David's online as well, but he should correct me if I'm wrong. Yeah, I think we basically saw that with taking the couple model simulation and then feeding that as a lower boundary condition to the atmosphere model, you get the same result as in the coupled case. So we had some confidence in it. Yeah. Yeah.
Can I ask a question?
Yeah, Kris, you have a question?
Yeah, I mean, my question, I sort of thought about during the talks this morning, and my question is for sort of from the perspective of what we talked about, but to the folks who spoke this morning. I mean, the Green's function pattern shows this amazing SST pattern that we almost never see. Like that would be a really weird leading mode of variability if you did an EOF analysis on SSTs at any sort of filtering period, or it doesn't really look like the trends. I mean, how do we really connect whether it's low frequency internal variability or forced trends to what the pattern effect procedures for the Green's functions, for example, are identifying as important patterns? Like, what does it say that we don't often see a big bullseye of an SST anomaly in the Western Pacific? That's just not what happens when you ring the Pacific bell,
So I see Maria and Christy kind of fighting over the microphone, but I also see.
Okay. So it's not actually a pattern. These maps you see, we call them sensitivity maps. It's not that this is a pattern ever acted out. It's if you perturb the surface there 1 degree. So it's to compare apples with apples within the model, but this doesn't tell you, it's not an EOF or anything which pops out of anything. It's not that the West Pacific warming is more likely or whatsoever. So you convolve that gigantic Jacobian with whatever SST pattern you feed into. And then you have to think of this one map, the sensitivity map, together with the evolving SST pattern as the actual product. Does this make sense?
Yeah, I get that. I guess I'm just thinking it's an area of low variance at most timescales. I get how the Green's function pattern it's not a pattern. It's identifying where the global mean is sensitive to local warming or SST anomalies, but it's a region of pretty low variance, like especially at the interannual time scale, which is kind of the lion's share of the variance in a power spectrum in the tropical Pacific. And yeah, I don't know.
So it's more like whatever SST pattern taps into even just a little bit, that West Pacific warm pool might even be 0.1 degree. It would be already very efficient.
Okay.
So I got to follow up. I had a similar, maybe a different thought, but along the same lines. So let's just say the model was off by a factor of 4. How would you know it was off by a factor of 4? Is there a way of verifying these simulations with observations or?
Simulations?
Pardon?
Simulations exactly?
Do you mean the patch experiments?
Yeah, well, you're looking at these sensitivities.
Say whether or not they are more or less likely. And you see actually a factor, not a factor of 4, but 2 between the different models in the West Pacific warm pool. It's huge. I'm thinking, I don't have the answer ready.
Yeah, I'm just saying that I had the sense that there isn't an easy way of assessing how accurate the model response to a change in local SST is. If you're changing SST in this one location and you see this huge signal somewhere else as you run the model, how could you say, is this reasonable? What can you do to have confidence that that's robust?
So an alternative way, maybe Jonah wants to explain, would be not to rely on these Green's function simulations, but you can construct a similar thing based on very long control simulations, regressing every point with every point, and this would gets you a similar information just based on the internal variability fluctuation. Maybe this goes into this direction. It's in practice very, very hard because the observations will be never long enough to get out that signal, but would be one way to test whether the models get the magnitude right, but not very practical way.
There's quick comments, since I feel like I was a bit called out on, well, we're seeing too many Green's functions. I think that's a good point. We can't test them directly. So what you have to do is try other things, like what Ben Sanderson suggested. Why not do a modal decomposition? So, as Maria and Jonah said, you could sort of think of these Green's functions as regressions, like straight up regression of radiation versus temperature. But there's ways around that. You can do principal component regression, where now you're regressing on the patterns that you're actually observing. Or you could do a Green's function weighted regression. So I think we do, if we really want to be able to compare this with observations, we do have to think of clever ways than straight up Green's functions. There's probably ways to use Green's functions as well in forward models, and you compare to observations in a likelihood framework. We're thinking about doing that as well, but that's sort of further away.
Could I jump in? So it seems like you can't observationally evaluate the Green's function itself, but you can evaluate the end product, which is the convolution of the Green's function with a warming pattern. And you can evaluate that against something like series observations, like interannual SST variability times the kernel should give you interannual variability in the T-wave fluxes. And I think UA showed that at least in model land, but I think Chen Zhou may have also done this with actual series observations. So it's one way of evaluating how well it works in terms of actually reproducing the TOA radiation anomalies over a given time period.
Yes, and you could formally do that in a Bayesian framework where you start by assuming certain Green's functions and then you evaluate how well they work based on how well the convolution matches observations. I see Rob there, so I think he's going to comment on what I was going to comment with respect to worm pool and variance.
Yeah, Rob England Wills, University of Washington. Wanted to back up a bit to what Kris was asking. I think this is a really interesting point that the area where you have this Green's function, this big bullseye, is not a region you have much SST variance. I think there's possibly a mechanistic reason behind that, in that if you have a SST anomaly in that region, it's going to lose a lot of energy globally to space. So then this would require a lot of energy to sustain SST anomalies in this region for any longer timescales than a couple seasons to years, maybe. So this is perhaps a mechanism why this worm pool is mostly in importance for maybe the forced response, and maybe the internal variability this poses a challenge too, because maybe then the internal variability does not give us a lens into what is actually, whether the Green's function is accurate or not. Maybe this region is only really, its warming relative to other regions of the globe is mostly coming out in forced response, and understanding how this relates, the warming in this region relates to other regions is something we have to understand about the forced response, that maybe internal variability actually doesn't give us a lens into this. And so that could pose a further challenge.
Yeah, thanks, Rob. That really helps with my question. I mean, I'll plug my poster one more time. What I said about low variance, I think it strictly applies to observations. In fact, if you look at long control runs from CMIP6 models and say, apply like a big low pass filter, like a 50-year low pass filter on like 500 or 1,000-year long runs, and then you just make a map of the variance of SST, actually the West Pacific warm pool actually does jump out as like the biggest sort of maximum of variance at these low frequency timescales. I have no idea why. So, yeah.
I think that might be a good place to stop, right? Unless there's
I did promise one online person
Okay.
opportunity. Yeah, so we'll take a question from Benjamin Sanderson, and then after this, we'll take a short break. I do see more questions, so online and in the Slack channel. So either bring the discussion offline to Slack or let it marinate until the breakout discussion later this week. So Ben, do you want to go ahead and ask your question?
Yeah, thanks. I mean, just really a follow-up to this discussion, really. I mean, I don't think we need to see the framing. I think we could imagine framing the Green's function in an EOF basis, and it really goes back to Maria's point as well. You don't necessarily need to think about deriving the entire response from a long control simulation on the grid scale. We can think about, you know, addressing what patterns of correlated warming that you see both under force change and in natural variability, and then addressing the problem in that subspace. And I really feel like that's a way to reduce the complexity of this problem and actually have something tangible. And secondly, I originally put my hands up in response to Clara's point, really, so this question of whether this causality in the AMIP type experiments. So the point's well taken that you get the same, that you can get the same feedback from a coupled simulation and from a simulation driven by the SSTs when you're in a single structural framework. But as soon as you have models from a different structural framework, or you have the real world SSTs imposed on in a model, then that guarantee goes away, right? And we can't guarantee that we're preserving the same causality loop that would be encoded in the SSTs which came from the couple model in the first place. Those were my 2 points.
Thank you. Natalie, did you have any other announcements before we go into break?
Nope. Nothing else other than, yeah, we have break and we back for the lightning talks. And I wanted to thank our speakers, of course.
So we'll go into about a 23-minute break. We'll join at the top of the hour, so 3 o'clock Mountain Time, for lightning talks from the online presenters. So this is your chance to interact with the online folks. We'll see you in 22 minutes now. All right, so it's 3 o'clock on my end, so I think we should start with the lightning poster talks, which will feature the virtual poster presenters. So we have a handful of lightning talks, which will be about 30 to 35 minutes today. Each presenter has about 3 minutes, and we'll try to have them up on the big screen, if not on these 2 little screens that you see them. So our first talk is from Tim Andrews. Go ahead and unmute and start your talk.
Okay, good. Yeah.
Yep, go ahead.
Okay, thanks. I'm Tim Andrews at the Met Office. So I just want to present a manuscript I have in review at JGR. There's I've made a preprint available, which I can share in the chat afterwards if you like. Oh, actually, I think, can you go back 1 slide? This is the second slide. Yeah, that's the first slide. So what we've done is created a new data set of AMIT PI forcing simulations. So we now have, so these are atmosphere-only simulations with observed SSTs and pre-industrial forcing agents with 14 climate models. That's a combination of Andrews et al. 2018, which was a CMIP5 generations, with the new CFMIP3, CMIP6 simulations. And we've also done 8 simulations where we repeat the AMIT PI forcing, but with HADIST1 SSTs as well to test sensitivity of the data set. So just a headline results really is the kind of previous multi-decadal variability and feedback parameter we've seen is robust. There's no big surprises there. The feedback parameters when you force the models with HADIST1 and AMIT2 SSTs are extremely well correlated. And for the historical period as a whole, it's about 0.2 watts per meter squared per K weaker with HADIST1 SSTs than AMIT2. For 1871 to 1980, so we split the historical record into 2 periods, really an early period and a later period, which corresponds to kind of the observed when we have the satellite observations from 1980 onwards. So when we have that big East Pacific cooling, we get a large pattern effect. And that's slightly weaker under HADIST1. But one of the key results is on the right-hand side here, which shows the feedback parameter against the abrupt force CO2 feedback parameter. And the grey is 1980 onwards. And that really ought to have been a desirable period for constraining climate feedbacks and sensitivity because it's well observed. It's got a large temperature trend attributable to greenhouse gases, and it sidesteps the aerosol forcing uncertainty. But here we show that not only are the feedbacks different when you force them with real-world SSTs from 1980 to kind of present day to the force CO2 simulations, but they're uncorrelated as well. So actually there's very little information about the future from the past recent decadal climate change. So that has implications for kind of emergent constraints which use the recent record to constrain the future. And if you move to the next slide, please. And just very briefly, this fits in very well with what Norman was just showing. We use the observed record, Deep Sea, which is series and Irby wide field of view stitched together from 1985 to present day, and just exactly as Norman was describing, we find that the feedback parameter, well, first it fits very well with the atmospheric models, but once you include the 2015-16 El Nino with large East Pacific warming, it reduces the feedback parameter by about 25%, so from about 2 Rossmead squared to 1.5. So it's suggestive that the pattern effect may be waning in the most recent data, and we really need to know what's going on in the tropical Pacific, whether this is just an anomaly over the last few years, or whether it's going to be sustained into the future. Okay, that's all I have to say.
Great, thank you, Tim. Let's go on to the next one, Hao Zhe.
Hi, everyone. I'm Hao Zhe, a PhD student working with Dr. Brian Soden. Here, I'm going to show a simple work that may change your current thoughts on the Gregory method. We already knew the Gregory method underestimate the ECS compared to the true ECS or the equivalent climate sensitivity. For example, you can see in the top right, the temperature normally at year 1000 is close to 12K, and it's still far away from the equivalent. The more than 6K ECS is larger than the 5.3K reported ECS for CSM2 from Gregory method. Current source usually attributed the underestimate ECS from Gregory method to the time-dependent feedback. For example, you can see in the finger showing the bottom right. Is this attribution correct? I afraid we don't think so. Here we would like to show the real cost. Of course, we think only with the schematic plot in the left with 1000 year CSM2 quadrupling CO2 simulation results. Yes, the feedback increased with time from the first 20 year to the 20 to 150 year and 100 to 150 to 1000 year. But if you focus on the two black lines, the solid line from the standard Gregory method, while the dashed line is constructed with lane warming corrected IF MIP EIF, and the best estimation of the final temperature change calculated using Lugenstein et al. Method. So here we have the general feedback slope we usually used and the equivalent feedback slope. And the interesting thing is these two share the similar slopes. So the reason for the underestimate ECS from Gregory method really is due to the underestimate EIF. As the EIF from the first 20 years is close to the most accurate EIF estimation, this lead to a thought on the true ECS calculation. Next slide, please. So here we provide 3 scatter plot to support the new idea of true ECS calculation from left to right are the evaluation of the EIF, net feedback, and the ECS. You could find more detail in our poster. Then I will just stop here, and I'm happy to take questions and any comments and suggestions will be appreciated.
Great, thank you. Next up, we have David Painter.
Hello there, hopefully you can see and hear me. Okay, so this is basically some work we have done with the GFDL CMIP6 model, and we're basically just trying to explore the kind of parameter space of estimates of ECS as a function of both different kind of forcing experiments and also the length of the forcing experiments here. So obviously just to try and get a little bit outside of the kind of single ECS value you can often get for a model from the 4 times CO2 experiment. So in all cases here, we also had fixed SST runs in order to estimate the radiative forcing. So that allows us to estimate the ECS in both the transient runs as well as from the instantaneous forcing runs kind of listed on the left here. And hopefully what you can see in the table is that we can get a very wide range of ECS estimates. Firstly, based upon the strength of the forcing. You can see as the forcing gets weaker, even over the shorter time period, year 1 to 150, you can see the ECS estimate goes down. But also as you glance across to the right of that table, and you see as we kind of do the linear fit to get the ECS over a longer period, the way the pattern effect kicks in seems to differ based upon the strength of the forcing. So you can see for the 4x CO2 run, the ECS estimate only goes up by about 1 Kelvin. But for the 2014 greenhouse gas run, by the time we're out at year 450, the change has almost gone up by 2.2 Kelvin. So there's quite a big difference here of state dependence, as well as also dependence upon the length of which the linear fit occurs. So if you go to the next slide, I don't obviously have time here to explain in detail, but basically what I show here on the left is an estimate of the feedback parameter for all of these runs in one place. So I basically just take off the effective radiative forcing from all runs at every time step, and then that then allows me to kind of show that actually all these runs actually fit on a kind of set line that shows a very kind of low estimate of equilibrium climate sensitivity. That's a red line on the left plot there. But you can see these other points kind of curving away from that red line, and that's the instantaneous runs. So basically what you go from is in the historical period and the AMIP runs, which are all included on those kind of points on the left there, it's followed the red line, to a certain time period, about year 50 on in the instantaneous runs, you see a huge change in the feedback parameter. And what the bizarre kind of animation on the right is showing is the radiative component of these gradients, whether I'm normalized or not normalized by the strength of the CO2 forcing. So if it's normalized, it kind of shows that this feedback parameter change, for example, on the bottom right, it's a short-wave cloud radiative effect, is due to a time varying thing. But if you look on the left, you'll see that's the long-wave cloud radiative effect. And when it's not normalized, everything kind of lies in a very straight line. My timer is up, so I guess I'm out of time, but I encourage you to look at the poster in order to learn more about this work. Thank you for listening.
Perfect, thank you. My timer is almost up too. So we'll go on to Nick Lutzko.
Hi, yeah, hopefully everyone can hear me. And first of all, I just want to say thanks to the organizers. I'm really excited for this workshop over the next few days. Unfortunately, UC is on the quarter system, so we're in the middle of classes right now, so I couldn't attend, nor Jack Bauchop, who's a student, a first-year student at Scripps, who's done some work which I think is hopefully really relevant to some of the discussions and that I'll be presenting today. So the question is, does the pattern effect depend on CO2 forcing level? Related to what David was just saying, as we crank up the CO2, does the pattern effect get stronger or weaker? To look into this, Jack took data from the long run MIT project, for which 4 models submitted runs with 2x, 4x, and 8x CO2. And so we have some Gregory plots here on the right for each of these different simulations. And then we've used various different methods to try to quantify the pattern effect, of which I'll present 2 here today. Next slide, please. So the preliminary result is that there's no clear relationship between CO2 forcing and the strength of the pattern effect. So in the top row here on the left is the are the feedbacks diagnosed using Gregory regressions over years 1 to 20 on the y-axis, and years 21 to 150 on the x-axis on the left, and years 151 to 1,000 on the right. The different marker styles are the different models, and the different colors are the different forcing strengths. So going from 2x in yellow to 8x in dark red. If the strength of the pattern effect depended on forcing level, for example, if it got stronger, we would expect all the yellow markers to be closer to the one-to-one line than the dark red markers. But in fact, we see you know, they're all kind of mixed up, and different models exhibit different behaviors. To try to quantify this a different way, Jack dug up a PhD thesis by Kris Karnauskas, who used quadratic splines to estimate forcings and changes in forcing over time. And the bottom left panel here shows the these quadratic spline fits to the data for the 4 models, where the black curves are the fits. And then the figure on the right, bottom right, shows the evolution of the feedbacks diagnosed with this method. And again, we see no clear trends across the models, and we have models on either end of the extremes in terms of the pattern effect getting stronger or weaker, or showing not much of a change. So this is preliminary work, and so the next steps will be to look into the actual patterns of temperature response and how they evolve. And it would also be great if people could get in touch if they have similar runs from other models available to us. And I put Jack's email address up here in case you want to get in touch. Thank you.
Thank you, Nick. So we have Lawrence Jackson up.
Hello, I'm Lawrence Jackson from the University of Leeds. I work as a postdoc with Piers Forster. My interest in the pattern effect focuses on its impact on near-term temperature projections. And the specific aim of the project I'm on is to try and develop a simple method for modeling or representing the pattern effect. Simple enough that it could be incorporated into a climate model emulator. The approach we've adopted splits the relationship between near surface temperature and top of atmosphere radiation into two parts. The first part fits a linear relationship between local top of atmosphere radiation and global mean temperature. The second part then takes the residual variation in the top of atmosphere radiation and uses maximum covariance analysis to derive relationships between the spatial patterns in the top of atmosphere radiation and spatial patterns in near surface temperature. And these relationships are expressed in terms of EOFs and associated principal component time series. And you can see some of the EOFs sort of illustrated in figure 1 on the slide. To illustrate the approach, we've used the AMIP PI forcing simulations from CMIP6. And just to briefly summarize some of the initial findings, what we're finding is that the maximum covariance analysis produces very spatially coherent EOFs for the temperature with good consistency across the 6 different climate models that we've looked at. The associated EOFs for the top of atmosphere radiation, however, vary much more between the models. Next slide, please. So if you take the pattern effect as sort of diagnosed this way, and you add it to a simple linear model of temperature and top of atmosphere radiation, what you find is that the variance explained improves in all 6 models. So that's the variance explained in the top of atmosphere radiation, and in particular for years 1940 to 1980 and post-year 2000. The pattern effect makes its largest contribution to top of atmosphere radiation using the second and third EOFs from the previous slide. And the common feature for these EOFs is that they all have very strong spatial patterns over the tropical warm pool region where deep convection is prevalent. Now this work is very much sort of a piece of work in progress. So the next stage is to take the diagnosed pattern effect changes at the top of atmosphere and to use them to derive near surface temperature changes, and then to incorporate this method into a climate model emulator. So I look forward to sort of any ideas that people may have and sort of any discussions that people would like to have during the poster session or afterwards. Thank you for your attention.
Thank you, Lawrence. Next up is Masa Watanabe.
Good morning. Hello. This is a work ongoing with my student Moki Saga and 2 more colleagues. Everyone in the room would acknowledge that AMIP PI forcing experiment was successful in isolating the time change of the feedback parameter during the historical period. But the question that was not answered with that run is the relative lower of the forced and unforced pattern effects, which were induced by the radiative forcing and internal climate variability, respectively. So we are trying to do a kind of attribution study using 50-member large ensemble simulations with MIRC6, not only for the historical period, but for the future projection based on a specific SST scenario. Here are 2 summary points, which I'd like to explain with plots. Next, please. First, we calculated the net feedback parameter for individual ensemble members using the conventional energy budget equation. Then we identified that the energy budget applies quite well to the ensemble mean quantities, which is indicated by the bracket. And this equation defines the forced component of the net feedback parameter lambda f. And simply we can obtain the unforced component by taking the difference between the first one and the second one. And the bottom left plot shows the effective sensitivity estimated for the period from 1970 to 2014 in the large ensemble. And you would see there is a scatter of the sensitivity of slightly larger than 1 degree, which is not negligible at all. And the sensitivity taken from the MPI forcing of Mirac 6 lies in near the end, lower end of the histogram, which is not surprising. But interestingly, the forced component of the feedback, which is shown by a red line, is very close to the sensitivity calculated directly from the 4 times CO2 run. And if you look at the time change of the feedback parameters, which is shown in the right, you see the purple curve, which represented the net feedback directly obtained from the ensemble, which has a certain spread. And the force component also varies in its strength in time before the 1990s. We think it is mainly due to the aerosol forcing, but afterwards we see that the feedback parameter is nearly constant and it's very close to the feedback in the 4 times CO2 run. And also the unforced component represented by the blue curve is not constant in time as well. And interestingly, it is negative most of the time period, the reason which we do not know yet. Thank you very much.
Thank you, Masa. Go on to Nadir, I'm sorry, I'm going to mispronounce your last name, Jivanji.
Jivanji, yes. Can you hear me okay?
Yes.
Great. Yes, this is some work kind of contrasting the conventional specific humidity-based feedbacks with the relative humidity-based feedbacks of Held and Shell. The motivation being that Held and Shell argued that these relative humidity-based feedbacks are more physical from a thermodynamic point of view. Here we kind of add to that argument by showing that these RH feedbacks are also more physical from a radiative point of view. Next slide, please. It'll just be an animation. So the methods here is pretty simple. We're just going to consider single column calculations, which are meant to represent a global mean. And these single columns have a fixed relative humidity of 75% and lie along a moist adiabat. And we're going to consider, we're going to compute spectrally resolved feedbacks, lambda sub nu. We can calculate these using line by line radiative transfer that resolve individual wave numbers. And the feedbacks are going to be calculated using partial radiative perturbations, where we just sub in perturbed atmospheric fields corresponding to the perturbed climate, water vapor, and temperature to calculate the feedbacks. Next slide. So here are the results, or just a sample of the results. So this spectrally resolved feedback in this mouthful of units, watts per meter squared per inverse centimeter per Kelvin. It's just the spectrally resolved version of the regular feedback, watts per meter squared per Kelvin. That's on the vertical axis, frequencies on the horizontal axis, and this is done in two ways. The conventional way on the left, and then with the RH-based feedbacks on the right. The total feedback is in black and is net negative, as we expect, and then the breakdown into different components are in the colors, and they're labeled as you can see in the lower left. And the first thing to note is that just by eye, the RH-based feedbacks are simpler. Next slide, please. In more detail, if you look on the left-hand panel, if you look at the conventional feedbacks, throughout much of the spectrum, so say from 0 to say 700 inverse centimeters, and again from 1300 inverse centimeters outward, the black curve, the total feedback, is close to 0. And what that means is that these other feedbacks, the Planck, water vapor, and lap strike feedback, in these regions actually cancel and actually constrained to cancel because of something that we refer to as Simpson's law, the physics of which you can read about in the paper. And so the conventional feedbacks actually have to cancel throughout much of the spectrum. And so you're sort of taking zero and splitting it up into positive and negative pieces in the conventional formalism. On the right-hand side, in the RH-based formalism, you don't have that. And in fact, because these columns have constant RH, both in the base and the perturbed case, there is no water vapor feedback. And in GCMs where that constraint is not enforced, the RH feedback, the water vapor feedback is still quite small. The other thing to notice is that the lapse rate feedback on the right-hand side, which is the orange curve, is just about negligible, even in the spectral integral. And that's important for the discussion here in this conference because already today the lapse rate feedback has come up. But what you see in these two panels is that the magnitude and importance of that very much depends on which feedback formalism you're working with. And so I look forward to discussing that with others over the course of this conference. Thanks very much.
Thank you. Next up is Diego Jimenez de la Cuesta.
If we look to a Gregory plot of a GCM 4 times CO2, please next slide, we note that the radiative response of the air is quasi-linear with surface warming. Next slide, there is a slight bending, the pattern effect, the feedback, the slope changes in response to the evolving warming pattern. Next. Some of you propose representing this effect as a perturbed ocean heat uptake depending on the efficacy epsilon, the H minus H prime depending on epsilon. Next, if it is larger than 1, leads to a weakening of the feedback, whereas if it is smaller, leads to a strengthening, as can be seen on the red and blue models. Next. Usually this term, next please, usually this term has taken as an ad hoc term that extends the usefulness of the linear framework. It has been pictured as a radiative feedback. Next. This is problematic in a nonlinear framework as it could mean that the planetary albedo or the emissivity depends on hidden variables in the ocean. Next. That is not only in the surface temperature and the humidity in the atmosphere. However, the changing ocean circulation can do this. Next. It redistributes the energy. Next. Changing the efficacy of the energy uptake. Also, next, deep water formation and upwelling connect the SST in the high latitudes and the tropics, contributing to the warming pattern and altering the radiative feedback. Next. Some of you have found those relationships between the Southern Ocean and the tropical SSTs somehow, but even the nonlinear conceptual model provides the hint. From a global perspective, this acts as a changing effective thermal capacity. Therefore, the total derivative of the Earth's energy is not only the change in the TOA imbalance, but also the change in the effective thermal capacity dC on dt. The ocean circulation modifies the warming pattern, ultimately changing the radiative response. Please, next. Solving analytically the model, next, the model proposed by Geoffroy and co-authors, I obtained for the first time an explicit mathematical expression for the evolution of the net radiative feedback in 4 times CO2 experiments. The time evolving part of this expression, F pat D, next, compares the energy content of the deep to the upper ocean, mimicking the role of the ocean circulation mentioned before. Next, using the CMIP5 and CMIP6 ensembles, this expression shows that the timescale for the strong bending is around 18 years in most models, providing a theoretical justification for the timescale of 20 years used to study the pattern effect. This highlights how important it is to constrain how the ocean circulation is modeled in GCMs. Thank you for your attention.
Thank you, Diego. Next up is Lily Han.
Great. Hi, I'm Lily Han. I'm a graduate student at the University of Washington working with Kyle Armour and David Battisti, and I'll show some super preliminary results looking at the relative roles of feedbacks forcing an effective heat capacity for higher transient warming in CMIP 6 compared to CMIP 5. So we know that less negative climate feedbacks drove a larger mean equilibrium climate sensitivity in CMIP 6 than CMIP 5, and also that larger radiative forcing in models with less negative feedback supported a higher range of ECS in CMIP 6 models. And thinking about transient warming, forcing, and feedbacks also contribute most to uncertainty in transient warming in GCMs, with a smaller role played by ocean thermal inertia. So we'd guess that climate feedbacks are also important for a larger transient warming in CMIP6 and CMIP5, but also wanted to look at the role of forcing and effective heat capacity here. So we used abrupt 4 times CO2 and pre-industrial control experiments, and here are shown averages centered around year 100 after CO2 quadrupling for everything except for the feedbacks, which use the full 150-year time series of anomalies. And we can see that larger global mean warming in CMIP6 models in black and the orange ensemble mean compared to CMIP5 models in gray and the blue ensemble mean. This larger global mean warming in CMIP6 is correlated with having less negative feedbacks, but also correlated with having reduced effective heat capacity in CMIP6 models. And it's unclear the direction of causality between the global mean warming and effective heat capacity. We don't know why the effective heat capacity is reduced in CMIP6, but one possibility is that this is supported by having a weaker pre-industrial Atlantic meridional overturning circulation in CMIP6 models compared to CMIP5 models, which is shown on the right. Next slide. So to look into the contributions of these different factors to increase transient warming in CMIP6, we can individually swap the ensemble means for CMIP5 and CMIP6 for the forcing, feedback, and effective ocean heat capacity, and use this energy budget to reconstruct the near surface temperature anomalies, which is shown on the right. We're looking at how each of these factors contributes to the total warming difference between CMIP5 and CMIP6. And we can see that the feedbacks in this blue line contribute most to increased warming in CMIP6 compared to CMIP5. But the punchline here is that looking at these orange and green lines for the forcing and effective heat capacity, these factors also play a role, especially earlier on. And the forcing and effective heat capacity combined contribute as much as the feedbacks to increased warming in CMIP6 over the first half of these abrupt 4 times CO2 experiments. So definitely preliminary results, and some future work might look at the role of covariances between these factors, also looking at swapping parameters in a 2-layer energy balance model, and thinking about why the effective depth is smaller in CMIP6 models. So my contact information is here, and I would appreciate any feedback. Thanks.
Thank you, Lily. Next speaker is Maofeng Liu.
Hello, everyone. My name is Maofeng. I'm from University of Miami and working with Brian Soden and also Vicky. I want to first thank the organizers for this exciting event, and there's a few of us in the morning. They asked about the role of the ocean in this pattern effect. Here, this work may provide some insights on this problem. What we do is like really embrace the pattern effect perspective, and then building on that, we really focused on incorporating the role of ocean, especially the ocean salinity in it, and try to develop a more general framework. And we use this framework to help understand the intermodal spread in cloud feedback and also climate sensitivity from the CNF6 coupled climate models. And if you look at the figure on the right, on the left, which is from a set of 40 CNF6 coupled global climate models. And here we are looking at the around 4 times CO2 simulation. And you can see that from the scatter plot, you really see a strong correlation between the global mean shortwave cloud feedback with the sea surface salinity roughly within the region from 45 to 60, which is in the Southern Ocean. And if you go down to look at the correlation spatial pattern, you can see that the strong correlation is not only seen in the local Southern Ocean, but also in tropics and subtropics, especially in the Southeastern Pacific region, where we get the largest contribution to the model spread in cloud feedback. On the left shows is a shortwave cloud feedback correlation. And if you look at the correlation on the right, which is showing for the total cloud feedback, there's a slight drop, but not much. The figure on the right, which is we use to help understand why there's such a statistical link between the two. We start with the ocean salinity. The idea is like the South Ocean salinity is a dominant factor that determining the ocean stratification or ocean density in that region, and that will drive the model's difference in ocean heat uptake there. And this ocean heat up difference then will drive a difference in the system temperature pattern. And this system temperature pattern difference is not only seen in the local South Ocean, but also is advected northward to the tropics and the subtropics. And then the spatial pattern effect will have to have an impact on the shortwave cloud feedback and then climate sensitivity. So it's like what we used to understand the temporal evolution of the cloud feedback or climate sensitivity can be also used to understand the models spread in cloud feedback and climate sensitivity. Next slide, please. So I will quickly go over the key result to understand this mechanism. The first one I want to show is this is a correlation map between the global mean shortwave cloud feedback and the zonal mean ocean density. Sorry, you can see a very strong correlation around this 60 Celsius degree, especially in the upper level. That's where the water began to subduct, which corresponds to the Antarctic intermediate water, or AIW, or sub-Antarctic modal water region. And next slide, please. And then if you look at the model, if you look at the model ensemble, you can see there's a strong difference in the first figure here. In the figure on the right here, you can see there's strong difference in the ocean density or ocean stratification among models. And from the figure in the middle, you can see this difference is dominated by their difference in simulating the ocean salinity, which is here we show the salinity contribution to this model's difference in ocean density. Next slide, please. And then those models with higher salinity in the South Ocean, and they have a weaker ocean stratification, and then they can drive like more ocean heat uptake. And this increased ocean heat uptake is stored in the deep ocean rather than in the relative ocean, rather than in the upper ocean. Sorry. So in the surface, so the soft waters in the South Ocean is actually cooler than those lower salinity models. Next slide, please. And through the enhanced the trade winds and this soft water, we believe it can have an impact in the tropics and subtropics, as shown in this system temperature pattern difference between these two groups of models. At the same time, we also see there's a difference in the lower tropospheric stability normalized by the global mean surface temperature, represented by the estimated inversion strength here. And these two patterns show very similar pattern here. I don't have time to go to the details, but the bottom line is both the system temperature and also the lower.
I think we lost your audio.
Yeah, for the, can you hear me?
Yes, we can hear you now.
Yeah, for the for the low cloud cover. Next slide, please. And these two, we believe, will drive this difference in the shortwave cloud feedback difference between the top and the bottom salinity models. Next slide, please. A beautiful thing about incorporating the sea surface salinity into this framework is that we can use that to immediately have like an emergent constraint on the cloud feedback and also ECS. And what we show here is we can, if you compare the black line and the orange line from the panels on the right, the emergent constraint can basically narrow the uncertainty in it, and most importantly, it argues against these high cloud feedback models and also the high ECS models here, which means that the models, the fresh biases in the models may play a role in why they produce much more higher ECS and also cloud feedback. I'll stop here. Thank you.
Thank you. All right, two more. So we have Geeta Prasad next.
Thanks. So I'm Geeta Prasad, an assistant professor from the University of Texas at Austin, and I'm trying to apply an aerosol climate interactions perspective to unpack the role that aerosols may play in the historical pattern effect. Next slide, please. And my starting point is that we've known for some time that aerosol forcing generates more strongly amplifying climate feedbacks than carbon dioxide does, but model uncertainty is extremely high around that. And this higher efficacy of aerosol forcing is generally attributed to aerosol forcing being concentrated in the Northern Hemisphere extratropics and the historical mean. Next, please. But a complicating factor for this historical mean picture is that the spatial pattern of aerosol emissions and aerosol forcing hasn't been static over the historical period. So there's been this migration in aerosol optical depth over the 20th century from the Northern Hemisphere mid-latitudes towards the tropics and South and East Asia. Next, please. And this creates this evolving spatial pattern of aerosol-driven SST change, which we can see in the right-hand panels here. And that modifies the all-forcing historical SST pattern over time, which is shown on the left. Next, please. And the big question that this raises for me is, what does that mean for the time evolution of radiative feedbacks via the pattern effect? So when we combine the time evolving spatial pattern of aerosol-driven SST change with the Green's functions we've been discussing, how much of the historical time evolution in the feedback parameter can we explain? Next. So if we look at the historical evolution of the radiative feedback parameter shown here, for example, from Dong et al. 2021, for the historical coupled simulations in black and for the AMIP observed SST runs in blue. Next, please. What would adding the historical aerosol only line to that look like? How much of the variability in the historical coupled line in black does that explain? And then next, as a thought experiment, we might also think about how wrong we would have to be about recent aerosol forcing or the nature of the response to the aerosols to explain this mismatch that we see between the black and the blue lines. Next. So in my poster, I introduced two studies that sort of obliquely hint at this question. Next slide, please. Great. So in a 2018 paper, I looked at the climate response to putting an identical amount of aerosol emissions from into one of the 8 regions shown here. So sort of a poor man's Green's function in CSM1. And I found a roughly 5-fold range in the climate efficacy of the aerosol based solely on where it's emitted from. And notably, some of the early 20th century aerosol source regions like Western Europe and North America have a much higher climate efficacy than emissions from present day and projected source regions like India and East Africa. Next, please. So in some later preliminary experiments, I've now explored how this scales up to a couple different global aerosol patterns. So I've taken the total global aerosol emissions in year 2000, which are in the center there, and put that amount of aerosols into either the year 1950 spatial pattern on the left or the projected 2050 spatial pattern on the right. So the same total emissions, but different spatial patterns, and then compared the climate response again in CESM1. And then next. And you do see some difference in the ERF and the temperature response and in the efficacy. So the year 2000 pattern there in green has roughly a 10% stronger efficacy than the other patterns, but certainly more work is needed, and we have planned to understand how robust this is, what drives it, and what it looks like over the entirety of the historical period. So my poster is in the virtual gallery, and at the top of the poster, I've put a Zoom link, and I plan to be in that Zoom link during the poster session right after this. You can also email me, but I really look forward to discussing this more. Thanks.
Thank you, Gita. So as Gita said, we do have about 60 posters on the online virtual gallery. So a lot of these talks are on there if you want to learn more about them. Their contact information is on the posters. You can also easily contact them through the Slack channel. At this point, I think that wraps up the virtual lightning talks. For the virtual audience, that also wraps up your day, and we will reconvene tomorrow at 8 a.m. for another round of virtual lightning talks. I'm getting a cue from Christy that he wants to make a couple announcements.
I think just one announcement that we generally don't have dinner, but today we do have food for the icebreaker. That's correct, right?
Correct. For the reception, there is like light appetizers.
So hang around for the posters, and after the posters, just transitioning into socializing.
It's during the posters.
During the posters. And I think that's it. We're not going to reconvene here. So whenever you're done postering and socializing, we'll see you all tomorrow in the plenary.
And then for those online, I've gotten a lot of questions about the recordings. I'll send you out the unedited raw videos when I get them in my inbox. And then the cleaned up versions, where we don't include the 30-minute breaks, will be edited probably in the next 3 weeks or so. So thank you all.